today. So today I want to talk about a paper cosmic attention. So the authors try to modify the attention or transformer structure to perform the uh, dynamics of chaotic system, especially for large scale prediction. So before proceed, let's read out the abstract. Okay, so did you find any gap sentence?
However, these methods face scalar challenges.
Yes. So the purpose of this paper might be predicting some trajectories of dissipative chaotic system. I will soon explain the word dissipative. But they face is often such system includes large scale system like fluid, chaotic fluid or something. So they often face such scalability challenges. So the authors try to overcome this issue by designing some transformer-based architecture. Okay, so let's go one by one. So in one sentence, the goal of this journal club is to understand how the authors modified the transformer architecture, especially for chaotic system. Usually, time series forecasting is performed, can be described by this such picture, but they try to adapt such mechanism into the examples like this turbulent fluid dynamics. Okay, so before begin, let's try to understand the very basic motivation of transformer. So in natural language processing, so imagine we want to translate a language. So for instance, imagine we want to translate French to English. So we have three words, je suis étudiant, and we want to translate it into English. I am a student. So in a very traditional way, people try to just embed the words one by one into something, some representation in the latent space, say. However, this has a problem because if you see this sentence, there is a word it, but this it, if you just embed it into a single representation, it does not work because the word it depends on the context. I mean, there cannot be a one-to-one correspondence. So running context is important. In order to have some meaning in the context, people developed what is called attention. Let me begin with the very simplified version of attention. Let's say I have an input language like this, but the computers need numbers, so we have to first translate it into the language of computer, which is numbers or vectors or something like this. This can be called embedding. For instance, each of these words or tokens are the vectors. Once again, having this embedding, we can update this representation so that they reflect the meaning of context that we want to focus. So, but how do we update this representation from X to Y? So simply we have a weighted average, which is the linear combination of the previous representations. Here, the alpha ij is called the attention weight, and the outcome is called the attention output. Of course, this is the very simplified version. How can we compute such attention weight? Attention weight first is simply computed from measuring the similarity between xi, each two tokens, xi and xj. It is defined by this inner product to vectors. But having just this inner product is not enough because we want to make it as a convex combination. So alpha ij should be summed to 1 and they should play like a probability. In order to do this, we once again put this similarity into what is called a softmax function. It looks like this blue graph. And for instance, if you have this numbers, then if you put these numbers into softmax function, they end up being like probabilities. Okay. Anyhow, attention is something like weighted average. So, since we measured its similarity, they try to reflect the relation between each pair of words. So that is how the transformer tries to input the context information. So as far as I know, there is even a vocabulary which is called the in-context learning. And this can be the start of such in-context learning.
I have a question.
Yes.
When you look at the index over here, so when you compute y sub I, you only look at from x sub 1 to x sub I, right?
X sub 1, I is yes.
So-
But this is not mandatory.
I see. So we could look at all the x's or x's before the index.
Yes. For instance, in time series forecasting, you see only the before, but you can see the word. Good. Okay, so such concepts, although it is originated from the natural language processing, can be applied for time series. So transformer is used for natural language. So natural language is sequence data. But you notice that time series is also a sequence. So conceptually, transformer can be used for time series. Just like this. This is an example. The time series is a sequence for each time. So let's say we have a time series. How do we do the time series forecasting? Let me just briefly explain. So let's say we have a time series, xi is equal to x of ti. Then as we did before, we first embed such number into another representation. Actually, in attention structure or transformer structure, we need the information on the position of such numbers. If we just have this xi, we don't know the location of each location of it, so we try to encode such information of its position. This is called positional encoding. How do we encode this? We can simply put the index I represent its location, or sometimes, especially for time series, people can put what is called the Fourier time feature, which is defined by this trigonometric series, because in time series it usually oscillates. So in the same phase, the values at the same phase can be regarded as the same position. So maybe that is one motivation for such encoding. Anyhow, having this encoding, we update our representation HI simply by adding this embedding and the positional encoding. Okay. Having such this, so before we used the representation to make a weighted average to create the attention, but this time we need actually one more update, which is called the priority value. So of course they all have some meaning in the context of natural language. But let us just think that such quantities are just multiplication of HI with some matrices. We have QI, KI, and VI from HI. And such matrices are the neural net parameters that will be updated from the input-output pairs. So having such quantities, we compute again the attention AI by this weighted average. Once again, it is the subnet function of QI and the inner product of QI and KJ. So you notice that the index I has the same with this attention weight, where the indices for key and value are J, which will be summed over. So this name is query. So we are curious about this quantity at I, which is attention, and we want to sum it over such key and values. Okay. Of course, after this attention, we need much more structures, but in a very simple language, we simply use this attention and plug in to the neural network, predict some future value. This is very simplified. For instance, if we have this data, we use some input and output pairs like this. And after using it, we move such windows like one step over, then the output window will be moved, translated again, and we use this such pairs again and again, and it's to update such parameters. Okay, this is the context of time series. Okay, so so far we moved from language to time series. Now we can move to the dynamical system. So what is a dynamical system? We often say that, we often classify dynamical system into two ways. First, in the continuous dynamical system, it is often described by differential equations like ODE or even PDE. Whereas the discrete dynamical system is defined by the recurrence relation like this. Xn plus 1 is equal to T of Xn. So two ways. Seems to me that usually in applied mathematics, people treat continuous dynamics, whereas in very pure mathematics, people also study discrete dynamics. Actually, discrete dynamics can be viewed as a time series, because every step we have numbers, we can treat it like a time series. So conceptually, forecasting can be applied also with such dynamical system. Of course, since it is forecasting, it is not completely rigorous, so there can be a slight error that we forgive. However, for instance, if we want to chaotic system, even a small error in the beginning will cause a lot of differences in the future. For instance, if you see this picture, you can see this blue dot and red dot. Initially, they are very, very similar. So with the error 0.001. However, if you see their dynamics, they are completely different. So this is one characteristic of a chaotic system. In other words, slight error meaning will be accumulated to a very large error. So how can we deal with this? So there should be a lot of efforts to deal with this, but one effort the authors did is what I want to say today. So they tried to modify some neural net architecture for such system. In order to explain it, let me first explain some core concepts in dynamical system that this paper here treat. First one is, of course, the chaotic system. Before that, I defined the dynamical system in a discrete way as a map, not differential equation. So F is a map from X to X. So if you can keep iterate it, create the dynamical system. What is chaotic? Actually, there is no precise definition of chaos. I mean, there is no consensus. This written by a famous mathematician. I mean, famous for me. But one common thinking is that chaotic system should have sensitive dependence on initial data. In a formal way, you can use some epsilon delta description to say that something, and initially although they are small, they end up explode their instances. However, this is not very practical way to describe chaotic system. In order to overcome this, people usually, especially in physics, adapt the concept of Lyapunov exponent. So let's say we have a map. So Lyapunov exponent is defined by some strange way like this. But if you can just look at this Jacobian, the derivative of this n iteration of f. So why do we define like this? So let's say we have a dynamical system. So xn plus 1 is equal to f of xn. If we just perturb it a little bit, we can approximate the perturbation of xn plus 1 by the f of xn plus some perturbation of f of some perturbation of xn. So if you subtract the two equations, then you obtain that the perturbation can be approximated by this derivative of this, the vector field of this dynamical system. If you iterate it, then you end up, notice that the difference in the n+1 time can be described by the initial perturbation with some nth multiple of this derivative. So the ratio can be approximated by some quantities. So that motivates some expressions like log or 1/n or something like this. This is not very important today. But what I want to say is that if such exponent, such quantity, the Lyapunov exponent is positive, then people define such system as chaotic. Let me give you an example. So, for instance, let's say we have a map from R to R, where f of x is cx. Then, since its derivative is c, you can notice that you just plug in c. The Lyapunov exponent, actually, it should be okay, so I'm a bit confused with the concept, but let me proceed. So Lyapunov exponent can be computed as the log of c. So if indeed if the initial data differs by some delta of x0, then you can compute the difference in the next step as I did before in the left side. Then you can iterate it until you find that this perturbation and at the time n can be expressed by the c to the n of perturbation initially. Therefore, if c is larger than 1, then you can see that such difference at time n diverges, so can be called as chaotic. Whereas if the c is between 0 and 1, then, so let's say if you plug in 1/2, c is equal to 1/2 in f, you can see that it converges.
I think Lyapunov is quite related to the entropy of the relationship.
Entropy of
There is also similar definitions. Looks very similar. The different relationship.
Oh yeah, sorry. Entropy means disorder, right?
Yeah.
And chaos kind of means you go to disorder too.
Yeah.
So I would think
Same.
not like same conceptually.
yes. Yeah. Maybe you're right. Actually, people study a lot of entropy in dynamical system, but unfortunately, I'm not very expert on this. Okay. But anyhow, thank you for your comments. So far we briefly discussed about chaotic system. Now let me go to the dissipation. What is dissipative system? Simply, it usually goes with the word Hamiltonian system. So dissipative versus Hamiltonian. What are they? So we usually say that dissipative system is energy decreasing, Hamiltonian system is energy preserving. In particular, Hamiltonian system is usually, it must be written as the following equation. where x and p represents position and momentum. And H is called the Hamiltonian, so can be described by the systems of ODE. And you can notice one thing that is representative is that along these dynamics, the function H is usually, must be preserved. Actually, if you compute this derivative by time, you can see that H is constant along its trajectory. For instance, if you record the harmonic oscillator, where the x-axis is time and y is x, you can see that this is Hamiltonian. If you draw the phase space, where x-axis is x and y is momentum, you can see that every circles do not overlap each other. In other words, if you start with one circle, you keep rotate with that circle. On the other hand, dissipative system does not have a specific form like a Hamiltonian system. But in dissipative system, there is some function which is called Lyapunov functional that is decreasing, not monotonically decreasing along the trajectory. For instance, there is a van der Pol oscillator, which is pretty much is dissipative, because in harmonic oscillator, as I just mentioned, if you start with a circle, you keep rotate the circle. On the other hand, if you start with some point, this van der Pol oscillator, you are absorbed to this blue line, which is called the limit cycle. Or if you start with some other places, you can be absorbed into another point. So, you can call that phase space is foliated in Hamiltonian system, whereas it does not foliate in dissipative system. The well-known circadian clock is also dissipative because the oscillation end up with the converted to the limit cycle. So what I want to say is that this paper deals with especially dissipative system because they want to end up focus on the attractor, something like the limit cycle.
The Lyapunov functional is minimized on the cycle.
Lyapunov function is minimized on the Oh, good point. Let me think. I think yes, but I cannot prove it directly. But well-known property is that if the energy in dissipative system, if the energy goes out, then they end up converged to Hamiltonian system as energy goes. So I think you're right, but I cannot prove it.
So if any system has such a decreasing function, and we call it dissipative.
Yes. It's quite, although I said that they are energy decreasing or energy preserving, the definition depends on specific function. Even in dissipative system, some function can increase.
Yep. So as long as there is at least one,
Yes.
there's no function that we call it.
Yes. Because there is a theorem, you may all know that. But there are some conditions of the Lyapunov function. There is a theorem that if there exists Lyapunov function, then the system converges to some stable equilibrium.
And well, it is true that Min pointed out the limit cycle minimize the optimal function value. If you track any trajectory, then you see that all the red arrows goes to the blue limit cycle rate. And that's how certain function decrease to certain value.
Mhm.
And on that limit cycle, the function L is a constant function.
Thank you. Yes. Okay, so then let me go next to the concept of ergodicity. So chaotic system is chaotic as its name indicates. However, if the chaotic system is ergodic, there can be some rule. What is the rule? So often it is very difficult to track individual trajectories. For instance, imagine you put some ink in the glass. If you put the motion of individual molecules, it's very difficult. However, if you study the whole distribution of the ink, it can be informative or informative. In terms of the mathematical language, you study the statistics or you study the whole probability or the whole measure. So this motivates the study of such map on the space of the measure. Let's say our dynamical system is T from M to N, and each space, the space M, is equipped with the measure, probability measure mu. First, we fix our discussion to study the measure preserving system. Let's say we say T is measure preserving if for any subset it satisfies that the following equation, which means that if it is such measure is preserved if they are moved by the such dynamical map. Actually, this is the push forward of U by T. You know the concept. So measure is preserved along the dynamics. So we constrain our dynamics or dynamics in standard curve to be measure preserved. Under this condition, we say that the system is ergodic if there is no non-trivial invariant set. In other words, if a subset is invariant, then it should be empty. I mean, essentially empty for the whole space. No non-trivial invariant set. What does it mean? Let me give you an example. Let's imagine a rotation by angle 2 pi alpha. For instance, if alpha is 1/3, then if you start with here, then it goes here and here and here again. It repeats the position again and forever. So this system is actually non-ergodic. It's not ergodic because if you take a small subset, I mean small neighborhood, including these green points, and such, and the three, I mean it duplicates into 3 parts, and if you take the union of such 3 segments, then it is invariant, but it is not empty or the whole thing. When you create the non-trivial invariant set of the system is not ergodic. On the other hand, if you take a irrational alpha, for instance, if you take 1/2 pi, then if you start with this, then you go like this, and end up it densely covers the whole circle. Actually, this system is proven to be ergodic. So, in some sense, the trajectories well covers the whole space. It's the intuition behind ergodicity. So there is an important theorem that the authors used in this paper. in ergodic system, we can say that one trajectory represents the whole space. In other words, time average equals to space average. This is Birkhoff ergodic theorem, which is written by Hwang. So the right-hand side is so f is any integrable function or the probability distribution function, something like this. And for any f, if you integrate in the whole space, then it is the space average because this is probability. The left-hand side, as you can notice, keeps following the trajectory of this initial data x. Because you iterate this with the dynamic system.
That is how we know that the system is ergodic.
How do we know that whether the system is ergodic? In practice, actually, as far as I know, it's very difficult. But there are many developed techniques, but I don't know that.
When can we assume that such systems are
You mean in real life?
yeah.
Real life. For instance, in the next slide, I will explain the notion of mixing. But mixing implies ergodic. So if the system is mixing, you can see that the system is ergodic. But I'm still not sure whether it is practical, and I'm not very sure whether real life systems are ergodic. That's one limitation of this group.
최근에 한 학생이랑 여학생이랑 무슨 모델에서 그 로지스티를 보여야 되는 사람이 있어요. 그때 라플 펑션 가지고 보여있는 게 있어서 그 펑션이 줄어드는 방향으로 막 스테이를 움직여가지고 어디 스테이트로 처음한다 이런 거예요. 보여더라고요.
You mean when we have a equation where if there is no equation, so you're asking about the case where we don't have equation. Well, one sufficient condition for ergodicity is a periodic and irreducible state of space. That basically means that once we start at a certain point, we can reach any points in the system. Right? We can cover the density of the whole space. And then there is no cycle or there is no oscillation. So, for example, if we have like long enough data and then the data looks covered almost all the states, and then there is no clear periods, and we would say this system is.
And if this theorem is contradicted, then we can directly say. So from the left-hand side, if you observe a single trajectory for a long time, as n is going to infinity, then it gives some information on the space. Actually, there is another version of ergodic theorem. So here, as you can notice, it is a pointwise convergence because we plug in x every time. However, you can reformulate it into an operator viewpoint. So for that, you can define an operator what is called Hwang operator G. It is an operator on the function of function. So if you get the input f, then you obtain the composition of f by the dynamics t. For instance, so let's say dk plus 1 is the dynamics, the trajectory of a particle along the dynamics, then it can be rewritten as this Hwang operator. We simply put t inside f.
I believe, in the example like statement,
Yes.
we have to replace T with F.
Then for TF.
So T of ZK plus 1 has to be replaced with F of ZK plus 1.
Ah,
So F of ZK plus 1 is G F of ZK or any F in the function space. That's a minor type.
I see.
So yeah, those two T's are replaced.
Yeah. Thank you.
So T is the
Dynamics.
dynamics we perform,
Yeah.
and F is any function.
That's correct. And this such relation that Dr. Hwang mentioned will be used in the construction of the author's architecture. Then, anyhow, you obtain the following relation. So for any functional, if you iterate it by Hwang operator, then you obtain the similar equation. So this can be a representative formulation of this ergodicity. And here you notice that for measure preserving transformations, the operator G is unitary. Actually, the unitary characteristic will be used as a constraint for their neural network. I will soon explain it. Next, let me talk about the concept of mixing. Mixing is something that is stronger than ergodicity. So formally, we say that a dynamics system is mixing if for any two subsets, we have the following relation. So the intersection of, so A is moving with the dynamics, but as the time passes enough and sufficiently, in some sense, the A forgets its initial condition so that such probability is given as a multiple of mu of A and mu of B. So for instance, mixing represents a system that is mixing. If this concept is too difficult, you can understand it as a decay of equal relations. So you can see that F and G are like a random variable. Then you see that the left-hand side minus right-hand side is really a covariance between F and G of T to the N. So this convergence means that such covariance goes to 0 as time passes sufficiently. So let me give you an example. So irrational rotation, as I just mentioned in the previous slide, was ergodic, but it is not really mixing because let's say that we have this A, the green part, and the B, blue part. So we fix B and we try to compute the moving of A along the dynamics. But if you imagine that A is rotating, sometimes they overlap and sometimes they do not overlap. So there is a possibility that mu of such intersection does not really converge it to their products. Of course, you have to prove it rigorously. So in other words, your original history keeps following. On the other hand, imagine that you have such dynamics from the interval to interval, given by T of x is equal to the double of x mod 1. So in a graph, you can describe it by this map. Then if you imagine that the inverse image of let's say 0.4 0 to 0.4, then you can see that the inverse image splits into two parts by such scaling map. For instance, if you have such subset A, then by such inverse image, it is distributed almost uniformly to the whole space. So you can think of this inverse image as it is distributed the whole space. So intuitively, if you start with this A and B overlapping a little bit, then end up you can imagine that inside of the B, A is almost uniformly distributed, so that if you compute the probability of this intersection, it is something like a multiple mu of A and mu of B, intuitively. This is the notion of mixing. And one thing that I want to say is that if mixing implies ergodic, the converse does not hold. Okay, so far we have we studied about 4 concepts. Now we move to the transformer architecture, how the authors try to reflect such characteristics. The data set they used looks like this. This is called the Kolmogorov flow or turbulent flow. It is often described as chaotic, but I don't know whether it is really proven to be chaotic. But anyhow, so this is the time direction. So the G1 represents the values at each time, and G6 and G11, something like this. But here, one thing I want to say is that in their architecture, transformer structure is imposed on space, not time. Time evolution is just a map, a different map. So if you see this whole structure, you start with input data, then the whole thing is the transformer structure. It gives some correlation along each space points. And finally, they put some unitary operator to move along another next step. So in an easy language, you start with some value at k, times at k. You create some feature map or some representation through attention or transformer, this whole architecture. And using the Kuhlmann operator or some time evolution, you evolve it once again, step again, to obtain the next feature. Finally, in order to recover the original value, you need a decoder sign. So we have 3 things: pi, g, and psi. Function. So let me present how did they create their architecture. First, I want to create the representation or the feature map pi using transformer. So here, although they are 2-dimensional, the value gk is defined on the grid, where each grid point is noted by this psi angle. Psi, I want to psi n. You recall that the attention is given by this weighted average. Actually, here the index is not from 1 to I. It is summed over the 4 index because they are space. They don't have order. So given the data, they define query key value as q, k, 3. And here, the one notable thing is that their positional encoding. So in attention, we need 2 things: embedding and encoding. In time series, they summed embedding and encoding. However, in their architecture, they embed the positional encoding to the attention structure by using what is called random Fourier feature. So if you define by this some trigonometric function like by zeta of I, Then you impose such positional encoding in the attention as follows. So here, let's look at here. So if you ignore this theta, then it is the usual attention weighted average without softness function. But here, they impose such information on the side, which is their position information. They try to impose such position in here, attention weights. Then end up it can be computed like this. So this means that their weight is larger when their positional information, positions are close, and when they are far away, their weight becomes smaller. So that's how they try to encode their spatial correlation into their architecture.
So in the previous time series example,
Yes.
they like was embedding and then positional
Yes.
encoding for calculating QV and P, but in this method they didn't use that.
In time series example, they create QKV and they create positional encoding and they sum it. But here somehow they are mixed.
Are the C values vectors or scalars?
Kushi is numbers, location.
Numbers like 1, 2, 3, 4, 5, or
I think if they are two-dimensional, they can be vectors.
1, 1, like 1, 5, and so on.
Why didn't they use just a like casual way to use project coding instead like practice focused? So
You mean why did they use it? Okay. Actually, they mentioned that one thing is that they used this random feature to give an inductive bias that this system is chaotic random, but it is not directly. They try to embed the chaotic characteristic in their architecture, although it is not very clear. That's one reason. And the other reason is that they mentioned that this somehow characterizes the mixing behavior. However, this is not also very direct. It's one more limitation that I think it is just intuitive interpretation.
제가 놓쳤는데 표시가 나타내는 게 뭐죠?
글씨는 이제 로케이션, 그러니까 Z가 홀 스냅샷이라면
네.
글씨 I는
스페이스 안에서
그 각각의 그리드가 있을 거잖아요.
제가
그리드에 있는 밸류들, 그러니까 로케이션을
when they should make influence of barcodes decrease.
yes.
What is the point of randomness? So do we sample the random values whenever we try to?
Yeah, random feature is not something that we obtain every time. Because I'm not. I don't fully get their point, but they try to use this. One reason for this is to make this correlation. Another thing is that they somehow think this randomness represents chaotic.
So maybe that there's no,
No, only this.
When is the DA extra? I will just. It's be like when we sample.
When do we?
Find 30.
Uh, when 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 we
진짜로 물결표 대응이 더 쉽은데 로테이션이 들어가야만
맞아요.
설립하는 거. 그래서 했던 거.
약간 자세한 유도 과정을 안 봤는데 그 캐릭터리스틱 모멘텀이 갖고 네.
그러니까 저 오른쪽을 어떻게 만들어 주려고
네.
했던 부분이 넣었다. 예,
Okay, so next, they argue that ergodicity is embedded by the unitary constant on the loss function. You recall that von-Neumann ergodic equation theorem is like this. And here, G is unitary operator if the system is measure preserving. However, one thing I want to say is that even though the system is not unitary, G can be, even though system is non-ergodic, G can be still unitary. So I will tell you how this is strange later. So we recall that our goal is to run the feature map pi, the time evolution G, and the decoder, sorry, this is psi, decoder psi. And the loss function they constructed is as follows. The first term represents whether this time evolution correctly captures the next point. The next term, L unitary, tries to impose the condition that eigenvalues of G are constrained on the unit circle. But this equation is wrong because I made a mistake because so you know that the unitarity is on the complex plane, complex number fields. However, in neural network, it is easy to work with real numbers. So what they do is to view the unitary matrix as a real matrix. For instance, unitary group U1 is same with SO2. They move the complex number into the real number. In that situation, the SO2 eigenvalues are constrained on number one, so there is some mistake on the equation. So you can view this as a transport. Anyhow, so far to summarize, they run the feature map phi through the attention, construct it through the attention, and they created time evolution whose unitarity is constrained by the soft constrained unitary, the loss function. And they also need to update the decoder psi. However, one thing I noticed that is strange is that this is the loss function equation in their paper. They don't have the information on the decoder. So maybe they just wrote it for simplicity or not. I don't know how they calculate the decoder. Maybe this should be applied once again with the decoder. Or maybe I missed it. Okay, so that's one point. So unitary operator, the eigenvalues should be constrained on the unit circle. So personal opinion, whether it's like this. And another opinion is that they argue that such unitary constraints constrain their dynamics to be ergodicity. But as I just mentioned that ergodicity is indeed not guaranteed simply by assuming that the evolution is linear. So this is another point. Maybe it's a neural network, so maybe it's very difficult to a lot of things rigorously. So the performances are tested in two different ways. First one is the short-term prediction. It is simply whether their snapshot data matches the true one using such relative L2 norm. You see these pictures. This is their method. And these are the error plots with the true one. You see that as the plots are more blue, then the error is less. For instance, if you see this column, you can notice some red plots with another method, whereas their method are or green or blue. They argue that their one is better. They also showed it in tapes. Their error is smallest. On the other hand, in the long-term statistics, they use many other criteria. For instance, they try to show that the KL divergence is the same. What is KL divergence? Is this like whether in distribution sense they matches the true one? And it turns out they argue that theirs was the best. And I just mentioned that there is a decay of correlation in the context of mixing behavior. They also try to quantify such correlation, autocorrelation, and they plot the graphs, see that they argue that their method correctly matches the decay of correlation with the true one. They also present the decay of correlation rate as a table. I didn't put it. And finally, they also tested whether such kinetic energy, which is defined by the scale of velocity, truly matches the true one. And if you see this error plot, you can also notice that the red area, which represents the large error, is smallest in their less compared to other. There are several limitations. As Dr. Choi mentioned, in real life, we don't know whether the system is truly ergodic. I'm not sure. And I'm not even sure where ergodic systems are sufficient in the real life system. I didn't think about it before. And there are other limitations further. And one thing that I want to emphasize is that actually their major contribution is to deal with the large scale system. And this is done by factorizing as a multi-tensor. This is another section, but I didn't include this for the time limit. Thank you for it.